Now I want to switch to binary outcomes. I just want to make sure that we're still recording. Okay. And I have to say, funding for this research was provided in part by the Advancing Healthier Wisconsin Research and Education Program under blah, blah, blah. Okay. So, so this question said one of the clinicians came to me. He was interested in seeing whether chronic spine pain is related to obesity. He had a strong suspicion that it was. Conversely, he didn't think it was a risk factor for neck pain. So there's a very nice survey called NHANES, and there's this arthritis questionnaire that asks all kinds of questions about neck pain and back pain, and I think it does some other types of arthritis pain, which not relevant. But there's 5,106 subjects were surveyed. Today I'm just going to restrict it to fairly simple stuff, just age and gender, and some anthropometric measures, weight, height, body mass index, and waist circumference. And there was some sampling weights to estimate for the U.S. as a whole. So that was a kind of a new twist, and I wanted to try that out too. Okay, so how do we do probit regression with BART? All right, so this is kind of a busy slide, so let's see. So there's this thing called the Albert Chib latent variable trick that all Bayesians should know and love. Basically, you have your binary indicator, and it's Bernoulli with some probability p. And then, so this p, we want to model this p by f, okay? So f is our BART function. The BART has the BART prior. I just want to move this cursor. Okay. Okay. So, so we have phi, which is the the standard normal distribution function, and we have some mu plus f of x. Okay. Well, why mu? Well, at one point we thought this was a good idea, but it turns out, I mean, you can specify this to be anything between. Well, you could specify it basically to be anything. Let's just stop there. But we found that playing with this doesn't really seem to matter very much, so for the most part, we just say mu is 0, okay? So we're saying that the data is centered at 0, and that seems to work fairly well, so I'm not even going to show mu in any of the rest of my talk. If for whatever reason you need it, it's there, but I haven't really found a good use for it. So anyways, so you create these latent z's, given normal with mean f and standard deviation 1. And if y is 0, then you truncate, then it has to be negative. If y is 1, it has to be positive. And then given the z's, the distribution of f given z and y is basically the same as the distribution of f given z. Because once you know z, you know y essentially, and vice versa. Sorry, not vice versa. If you know y, you don't know z, but you get my point. Anyways, so basically this boils down to a simple Bernoulli likelihood, and basically we're back to a continuous BART with unit variance 1 and zi are the data. Okay? It's beautiful. It's beautiful, right? It's my favorite trick. Okay, so here's another nice trick. This is Friedman's partial dependence function. Okay, so now we've got a bunch of x's, let's say, and so f is of x, but x is this x has a lot of x's, right? So there's some subset of x of interest, and the rest called the complement we don't care about, right? So basically the trick works like this. F of x of s, you can take the expectation over x of c, given x of s, which are held fixed, or they're conditioning on them, they're not random, and you just take this expectation. Well, how do you do that in practice? Well, in practice, we just sum over the cohort. Okay? So, and you do this at each step of m. So I'm saying the MCMC steps are subscripted by m. So at each step, you have this random draw of f, and it's just on those parameters. And at the end of the day, you want to average all of those to get some overall function. This is the typical Bayesian estimator where you just average over the samples. See, and they say Bayesianism is so hard. Look at that, it's easy, right? Okay, so I suppose if we were really smart, we could have done all this in WBART, but I decided not to do it that way. I created a different function called Pbar. Okay, so it looks pretty much the same as what we had before with WBART. Yeah, in fact, it's identical. There's a Pbar and MCW, it's exactly the same. The inputs are the same and the outputs are the same. Now, the outputs mean something different, but they're the same. You know what I mean? And we can do the predict, and again, it's the same, right? In fact, in this case, it's almost exactly the same. You're just putting in an object of different type. You're putting in an object of type Pbar instead of WBART. And I was going to do a Lime demo. I'm a little bit behind, so I'm just going to show you the results here. So this is back to the chronic pain and obesity. So I did Friedman's partial dependence function. I fit with all those variables I was talking about. So I fit. So if the patient got to say yes or no whether they had chronic neck pain, and I fit to all those variables: age, gender, weight, height, BMI, and waist circumference. But I figured, okay, BMI is good enough, right? Let's just summarize it for BMI. So I use the partial dependence function, and this is what you get. I think red are women and blue are men. So what do you think of that? Generally, anything over 30 is considered to be obese. Actually, this is kind of an interesting sample. I don't know how this happened. If either America is just chronically overweight now or what, but we had people, we had lots of, in fact, we had, the majority were overweight in this sample. Now, I don't know if that happened by accident or on purpose, but anyways, it doesn't look like there's much going on, right? So if you're heavy, don't worry about your neck, right? It's going to be fine. But with back pain, there's some trouble. And it's not just the heavy people, it's actually the frail people too have a higher probability of having lower back pain. So if you're frail, it's up here about 30%, and it goes down. And actually at 30, which is I think where overweight starts, it's actually not too bad, but then it starts going up dramatically once you hit 50, and then it's flat. I think what's going on here is there are some people out here, but not a lot of them, thankfully. But there's a couple. And it's pretty much the same for both men and women. It's almost parallel. And that's coming from the data. There's nothing in the model that says it should be parallel. But it's parallel, but notice there's a gap here, right? Yeah, I think red is women. So women are at higher risk. Oh yeah, it says right here. So women are at higher risk. Let me see. Yeah, they're at higher risk for neck pain too. I don't know what's going on there. I think women are at slightly higher risk for arthritis too, but that's just a guess. Does that make sense?
Doesn't that bother you that they're exactly parallel like that? Even though that is the data?
No, I mean let the data speak. That's my job, right? We're working on it. No, it's not out yet. Actually, I showed this to the clinician. He said, "Oh yeah, that's what I thought." No, thank you. No, nothing.
I have a question about your, on the y-axis it has phi of f of x, and your original equation was phi of mu plus f of x. You said that the grand mean mu in this case doesn't seem to matter very much. You played with different ones.
No, it matters, but I'm saying okay, the mu is a constant. It's not anything random. So you can put in anything you want in there. But I've tried this many times, and it doesn't seem to make any difference. Like you can put -1 in there, you can put plus. I mean, you can't go too crazy, right? It can't be outside of, -5, between -5 and 5. But the idea that it was going to be sensitive to that it doesn't appear to be the case.
Well, when you, when the continuous part was explained, it was saying that the grand mean mu was subtracted off from the data so that the means of the tree nodes could be, it could have a prior that influenced them to be pretty small, like close to 0.
Yeah.
And wouldn't the mean of the
But you can't center binary outcomes. There's no way to center it. So it's kind of a different animal. Now, we thought it would work the same way, but it actually doesn't. It's slightly different, but it's fairly close, okay? I don't know what more to say about that. It always confuses people to have it there. So maybe I should just stop talking about it and just say mu is 0, and then we would have just avoided 5 minutes of conversation.
So here, have you run the model twice, like separately for males and females,
Oh, no,
or you just added?
One fit.
Okay, so how did you add that interaction term? It was just.
BART did that.
Okay.
It figured it out. Yeah. It's smart. It looked at the data, saw that there's something going on. Actually, it's not much of an interaction, though, really, is it? It's more of a shift, right? They're fairly parallel. I don't know. Anybody else want to say anything about that? Prakash, you look excited to say something. Yeah.
Well, it's kind of interesting how you look at interaction. In a typical, say, probit model, if you had fit, the interaction would be on the probit axis, right? So you move, there's which has a very different interpretation on a probability axis.
Yeah, that's true.
Okay, and it's the same thing with the logits. When there is an interaction term, what does that mean? That's not, but this, you don't have to worry about. You can directly have interpretable quantities that are sitting in front of you and see that on the probability axis, from men to women, there is an increase, and that increase seems to be free of what the BMI is. And if there were interactions, like heavier men had more pain or whatever, it would have figured that out.
I mean, yeah, and also I would add is they're not entirely parallel. I mean, you can see there's a little wiggle, but not a lot. And I didn't put credible intervals on this. I probably should have, but.
And also, I guess once this is rescaled, once this is rescaled, the lines will no longer be parallel if they are rescaled to original axis.
What axis? What original axis?
I think they've been back transformed to the correct
Yes.
BMI plot that he's showing you.
Yeah, the
Exactly.
probabilities on the y-axis and BMIs on the x-axis.
Right. So this is I think one of the advantages of, Bayesian method in general, but in BART in particular, is that you don't have to worry about transformations, and Dr. McCullough mentioned that earlier. And this is, you can put it on an axis, on a scale that you like, or your physicians that you're interpreting this for, they like. So these are the no odds ratios here to necessarily talk about. You can, if you want to, by the way. Odds ratios are functions of these, so you could plot that.
Oh yeah, you could take the.
So you can just take every sample
I'm gonna show ratios
and
later.
turn it into odds instead of probability.
I'll do that later.
So you could, yeah. So that's the freedom you have.
Yeah, lots of freedom. Okay, you got to turn off your microphone. Okay, so this is something the reviewers are always giving me a hard time about. Oh, we don't like Probit. You got to do Logistic. Logistic is so much better than Probit. And like, how do you know what is going to be better? It's like they have this crystal ball and they know what is the right answer, I guess. But now we can. So we added Logistic with the help of Robert Gramercy, who's been working on this. And it's basically the same kind of trick. The difference here is now the variance is not 1. The variance is 4 times this psi squared, where psi is a member of the Kolmogorov-Smirnov distribution, which is a devilish distribution to sample from. Luckily, DeVroy has a book on this, which is freely available. You just Google it, and he explains how to sample from that. And but it's not trivial. But we did it, or I should say, Robert Gramercy did it, and it's in the package. So now it's the same kind of thing. We've got continuous BART.
Check the battery.
So anyways, I was so happy to stick it to that reviewer, and I said, hey, we got it in the package now. So we got it in time for me to reply to him, so I was so happy. Okay. All right, so Rob just showed you a continuous, checking the convergence is trivial, right? You have this nice variance parameter, and you just watch that parameter and see what happens. It's awesome. Well, guess what happened here? Where's the variance in binary BART? No variance, right? No variance. Yeah. So I went back to Goecki. Anybody speak Dutch? I think that's how you pronounce it, Goecki. So Goecki, this is what, in Bayesian survival analysis, this is what's typically used as Goecki. So let me take you through this. It's a fairly old trick. It was alluded to by Hastings way back, and then Silverman, I think, made some improvements. So basically the trick looks like this. Okay, so this is your typical Bayesian estimator. You have our favorite Greek alphabetic letter, theta. So you have something, and you just average over the samples of that, right? But now, for this, you need what they call the asymptotic variance. So if the limit goes to infinity of the variance of our estimator, we need to know what that is. Huh. Well, okay, so I think this is what Silverman's trick. So you pretend that these draws are from an ARMA process. And then there's this there's this formulation they call the spectral density, some sort of characteristic function, right, Prakash? And, but basically, I think that goes away because actually what you do is you plug in 0. So I think that it takes this out, right? Anyways, this is all done by software. That's why I'm not up exactly on the theory. I can follow it, but I'm not a big time series guy. So, anyways, so this asymptotic variance is estimated by this, and you know, for time series they've been doing this for decades. This is nothing out of the ordinary. So Goecki came along, and he said, okay, now this is how you're going to do it. So you divide your change into 2 segments, A and B. So the A segment starts at the beginning, and the B segment is towards the end, okay? So there's these two fractions, A and B, and they have to add to less than 1, and Gowecki suggests A is 0.1 and B is 0.5. And I don't remember how he got that, but you can change that, but that's the default in our package. Okay, so now you have two estimates. You've got estimate from the A segment and estimate from the B segment of both the mean and the variance. So you can do, it's just a normal test, okay? Like so. So those Z's should be distributed normally. Okay, so we have a Zi corresponding to each theta I, where theta is, generally it's some function of f of x, right? Because what else do we have, right? We have no variance, we've got nothing else, that's it. Okay, so we created these functions, Gowecki diag, based on the CODA package, and then there's two examples. So if you use the system file command and you put in this file name, package BART, and R tells you where that file is on your system so you can run it. Or you can run it directly from the demos package, but I don't like running it from the demos directly because they make you prompt after each plot, which I find really annoying. Okay, so let's see here. Yes. So here are the two examples, okay? So n is 100, 1,000, 10,000. Am I getting feedback here? Is it too loud? I'm getting an echo. It's like the voices in Rob's head are talking to me. So k is 50, and by k I mean the number of variables. So again, this is Friedman's 5-dimensional test function. More or less, I've tweaked some of the settings. Anyways, so the Z's are generated like this. Zi's have f of x as the mean, and the y's are just 1 if z is greater than 0. So here I'm generating the Z's. So I'm doing a reverse Albert Chib trick, I guess. Okay, so this is what these are the 4 plots that the example creates. So x4 should be pretty much a straight line. Let me just put x4 up again. So x4 is just a linear term. So I'm keying off of that. So this is simulated data, and we know what the truth is. We know this should be a straight line. Okay, but with n 100 and 50 variables, it doesn't get very straight, right? So, I mean, that's sort of the nature of the beast here. What I'm really concerned about is, did it converge? So here I'm looking at the, so what I did was I picked 10 subjects, and I'm looking at their ACFs. So each subject has a different color. Okay, so I'm looking at the ACFs of those patients, subjects, sorry, and also have 10 of their trace plots. So it looks like it's moving around pretty well. So on the y-axis here, I have the probability, and these are the samples. So it's moving around pretty good, and very low autocorrelation, right? I mean, it's virtually nil. But those are the typical ones. Also, I've got the Gowecki Z's here. So I'm plotting them all, and you can see, generally they're between the cayenne lines. So that's fairly good convergence. It's good convergence even though it didn't get the right answer, because sometimes, the data is what it is. We just don't have enough information in the data to get the right answer. So now if we boost the sample size up to 1,000, now we have a lot more information and we nail it, right? You can see autocorrelation increased slightly, but nothing to be concerned about here. And the trace plot's still moving around okay. And again, most of them are between these two lines. Actually, since we're dealing with 1,000 now, we should be using the blue lines, right? So very few points outside of the dark blue lines. Okay, so this is how you use the Gawecki chart for a binary BART to determine if you're having convergence issues. Okay, we get to 10,000. Okay, so look at that. It's nailing the function now. Dead on, right? But look at the autocorrelation. It's increased dramatically. Look at the trace plots. Not moving around too good, right? Look at the chart here. So now we should be looking at the green lines, but look at how many are outside of the green lines. This is not good. So what's going on here is that for very large data sets, BART is not exploring the whole space. See that? It's not exploring very tiny moves. Okay, so what do we do about this? Don't have large samples? Large samples are good, right? Look how I'm nailing the answer, the true answer. Okay, so there are some theoretical countermeasures, and this is one of them. So what I'm going to do is I'm going to take some random samples of the data. I'm going to randomly partition it into 10 sets of size 1,000. I'm going to analyze the 10 training sets independently, and then I'm just going to combine the chains. And then I'm going to look at the convergent diagnostics. All right, so this is what it looked like without countermeasures. So I'm just going to flip back and forth. What do you think? Good? I'm pretty happy with this. Still nailing the effect, but very low autocorrelation, very good travel of the trace plots, and the Gawecki chart is vastly improved. See, very few outside of the green. Remember before there was even lots of them outside of the red. I see you stunned. All right, so I forget what the next one is. Oh, so and I just wanted to compare this with, so these are 10 samples of N of 1,000. So I was just curious, how does this compare to N of 1,000? It's kind of, it performs a lot like N of 1,000. Of course, there's more points in the Gawecki chart, so it's a little deceiving. But if you look at the others, I think you get the same type of performance. So basically, what we've done is we've improved the performance from an N of 10,000 to something like what we would have for an N of 1,000. Oh, that's it. Any questions?
Do you have any possible clues as to why why too much of a sample size, too many samples is hurting you?
Yes and no. So Rob might want to jump in, but his idea was that it's hard to, so like, we have those tree proposals. So his thinking was that those proposals are being rejected a lot, so it's kind of sticking. It's very sticky movements. Yeah, any comment? Can you use your microphone? It might get picked up on the audio. I don't know.
I'll just yell.
Oh, that's not going to work.
Again, in some sense, this is kind of a simple version of BART. There's more complicated moves. This one is based on mostly the first step. Just add to, fill to. I think that might get a little sticky with the again. So there are other moves that we're going to be incorporating. We'll kind of tweak it a little bit. But probably that's all.